Welcome to Study Loop.
So we're dealing with a transverse wave now, which starts out at time t equals 0 in its maximal displacement at x equals 0. We're given a velocity 8 meters per second, an amplitude 0.07 meters, a wavelength, and we're told that it's traveling in the minus x direction. So it's going backwards compared to what we're normally used to. So we're told we want to find f, the frequency, the period, and the wave number, k, ft, So first off, let's find the frequency, and that's pretty straightforward. We just use our equation v is lambda f. So f is going to be v over lambda, which is 8 meters per second divided by 0.32 meters, which numerically turns out to be 25 hertz. Then we can use our handy relation here. The period t is 1 over the frequency, which is 1 over 25 hertz. Here you go. And then that is going to be 0.04 seconds. Oops, let's write this in black. To at least be consistent if we're going to be random. And then we're given k. Is 2 pi over lambda. And we're given the wavelength here, so this is just 2 pi over 0.32 meters, which is equal to 19.6 radians per second. Great. So moving on to part B. Oops. We want to write the wave function describing the wave. So that means so if this is the y direction, we want to write y of x of t. So remember that for traveling transverse waves, traveling in the plus x direction, then our equation is a cosine kx minus omega t for the positive direction. So this t is going to be opposite of the direction that it travels in, this line. But for the negative x direction, which is what we're dealing with, we have a cosine of kx plus omega t. And we calculated k up here, and remember that omega is equal to 2 pi f. So our function y of x of t then looks like this. It looks like our amplitude 0.07 meters times cosine of, because there's a 2 pi in front of k, then there's a 2 pi in front of omega. I'm going to write this as 2 pi times x divided by lambda. So x divided by 0.32 meters minus the frequency, 25 hertz, times t. And we're going to simplify this with numerical values. So we multiply this, and that's going to be equal to 19.6 inverse meters times x minus 157. Oops, let's make this a little neater. Radians per second times t. So forgive me, it's a little messy, but this is our answer for B. Now moving on to part C. Let's start a new page here. We want to know at position x is equal to 0.36 meters and t is equal to 0.15 seconds. What's y? So we just plug it. It's just plug and chug into the equation that we just made. And in fact, I need to go back here and correct these. Minus signs should be plus signs. Forgive me for that, because we're moving in the minus x direction. So this is going to be, if you plug in x and t, you just plug this number into here for x and this number in here for t. Then I'm not gonna make you sit here and watch me write out the numbers. This is going to be positive 0.0495 meters. Great. So then it asks, finally, we want to know how much time is between this point here, 0.15 seconds, until the particle at x equals 0.36 meters has maximum upwards displacement. So a maximum upwards displacement means that y is equal to a. So I'm going to say specifically we know where the particle is in x, so y of 3.36 meters t is equal to the amplitude here. That's what that means. It means it obtains its max value, which is the amplitude. That's what the max displacement means. So what we want to know is, when does that happen? How much time after 0.15 seconds does it take for this to happen? And since we know that y of x of t is equal to a cosine kx plus omega t, this is equal to a when cosine of this is equal to 1. And we know that cosine of theta is equal to 1 when theta is equal to n times 2 pi, where n is some integer. So 0, 1, 2, ... or even -1, -2, -3, etc. So what we need to pretty much find is when kx plus omega t is equal to n pi, but also when at a time after 0.15 seconds when this has happened. So let's get going. So we know that 2 pi times x over lambda plus t over the period here is equal to n times 2 pi. Great. And so if we plug in some numbers here, that means, well, first let's solve for the time, because that's what we're trying to solve for. So t is equal to big T, the period, times n minus x over lambda, which when you plug in numbers is 0.04 seconds, times the integer we're looking for, so all I'm doing here is trying to solve for n, the integer, so that we can solve for 2 pi. So basically, what this does is says at every time in this equation, for n equals 0, 1, 2, 3, 4, whatever, you're going to get a time when we're at the maximum upward displacement, because the wave is going to go up and back and up and back. So we're always going to find some times that are going to give us a maximum upwards displacement. But we're looking for the one closest to this time here, the 0.15 seconds, but also that's occurred after it. So if we try to guess and check some values for n, if we try n equals 4, then that gives us t is equal to 0.115 seconds. So that's before our 0.15 seconds. But if we try n equals 5, that gives us t is equal to 0.155 seconds. So that's occurred after. So it's asked, recall that the original question says how much time has passed since this time for it to reach its maximum displacement. So the time passed, or time elapsed, is going to be 0.155 seconds minus this time here, 0.15 seconds, which is 0.005 seconds. So that's the time elapsed. So I know this is really complicated, so I'm just going to do a quick summary of what we did here. So we're told that we're at a given x position, right? And so at a given x position, the particle is just going to look like it's going up and down and up and down. We're given some time in this motion, 0.15 seconds, and we want to know how long, if this is 0.15 seconds, how long does it take for it to get from here to its maximum point? So in order for it to be its maximum point, we know that cosine of kx plus omega t is 1, and that means cosine of this whole thing, that means this whole thing in here has to be some integer times 2 pi. So we've solved for the time such that this whole thing is some n times 2 pi. And so that time here has to be equal to this expression here for any integer you want. So when these two things are equal, when you plug in an integer, that means we're going to be at a time when we're at a maximum displacement. So then we found the integer that gave us a time that occurred after this, but not too far. So the next closest time after this. So I know that's a little bit involved as a problem. So I encourage you to look through this again, give it as many tries as you need to fully understand what's going on. But it's mostly practice with trig and understanding the form of the wave equation. So that's this problem.